Hello, everyone. Welcome to Pre-Lecture 13. This is getting us into Chapter 14 in our textbook, and we're going to be discussing acids and bases. Something I do want to say is that we will finish up with some problems from Chapter 13 on equilibrium in class on Tuesday, so just be aware of that, but we're going to get into the concepts of acids and bases in this pre-lecture. Okay. So why do we care about acids and bases? I mean, at a basic level, they make up many of the foundational chemicals of our society. They're also very useful for modeling a lot of more complex chemical reactions. And so if we just think about water, it can dissociate into smaller parts consisting of protons, or H plus, and hydroxide, OH minus. So if we just split water, we can end up with H plus and OH minus. This gets into one of the definitions of acids and bases. So hopefully, well, I can't remember if you covered this in Gen Chem 1. If not, we'll cover it now. So this is the definition of a Bronsted-Lowry acid and base. So a Bronsted-Lowry acid will donate a proton, whereas a Bronsted-Lowry base will accept one. Okay. And so when you do this, we get what's called a conjugate acid-base pair. And of course, conjugate acid to base pairs means that we need things as pairs. And so essentially what we would think about if this is our chemical reaction on the bottom, our acid and our base are always going to be our reactants, and then our conjugate base and our conjugate acid are always going to be products. So if you see the word conjugate, that's referring to a product. Okay. The thing that will be behaving as an acid on our reactant side is going to be end up as our conjugate base then, and then vice versa, to where the thing that is acting as a base on our reactant side is going to end up as a conjugate acid. Okay. And so in this example here, we have water and ammonia. So if we think about the forward reaction, water is acting as an acid because it donates a proton. One of these protons ends up over on the ammonium that is our conjugate acid, whereas ammonia acts as our base because it accepts a proton to again form that ammonium and that hydroxide. Okay, so that is a conjugate acid-base pair defined in terms of Bronsted-Lowry acid and base. Okay, so take a moment, think for yourself in these two examples, which of these species is going to be acting as an acid and which is going to be acting as base. So if you want to take a moment to think about that, then I will go ahead and go on right now. And so hopefully you were able to identify that HF is our acid because that's going to donate a proton over to here. Water is going to act in our base as a base in this situation. So we end up with this H3O plus, a molecule called hydronium, and then fluoride as our base. In this case, we have an organic molecule called pyridine. And in this case, water is actually going to act as an acid. So water has a property that we'll talk about later that's called amphotericity. Basically, it can act as an acid or a base. And so in this case, water acts as an acid. We form pyridinium and we form hydroxide. Okay. So here's our vocab word. So water can be amphoteric, meaning it can act as an acid or a base. One of the very important things that we're going to be talking about in chapter 14 is water's autoionization constant. And so this just happens in water. If you have a glass of water sitting somewhere, this is something that is occurring constantly, where when we have 2 moles of water or 2 molecules of water represented here, they will actually autoionize to where we will start with 2 moles of water, we'll end up with 1 mole of hydronium, 1 mole of hydroxide. Okay, and so we could also represent it with this chemical equation here. And we can write its own equilibrium expression. So Kw is what we identify this process as, and it's still products over reactants, but because water is, of course, a pure liquid, we don't include it in our equilibrium expression. So Kw is equal to H3O plus times OH minus. Okay. And so this will become important anytime we're going to try and identify the pH of something. And so if the amount of protons and hydroxide are equal in our solution, then that is neutral. If we have more protons present, we identify the solution as acidic. If we have more hydroxide present, it is basic. And so how we generally then have a shorthand way of identifying which has more, or which, if a solution has more protons or more hydroxide, is generally pH. And so anytime you see a lowercase p, that is a math function, shorthand for a math function. P just means take the negative log of. And so pH means take the negative log of H plus or H3O plus, which are the same thing. And so pH is the negative log of the concentration of hydronium. If we were to, of course, undo that, or for example, if I gave you the pH and asked you what's the concentration of hydronium, you would do 10 to the negative pH to undo that function, okay? Likewise, we can also calculate the pOH, so that, again, P function just means take the negative log of the concentration of OH or hydroxide, and it's the same process to undo that P function, okay? Crucially, and this will be a big point that we'll also review in class, is we can use Kw, so again, our concentration of hydroxide and hydronium, and we actually know the value for that. So that Kw value is 1.0 times 10 to the negative 14th. And so in neutral water, we know that we should have a concentration of 1.0 times 10 to the negative 7th for both hydroxide and hydronium, okay? And if we're thinking about things in P functions, pKw is 14, which is also then equal to the pH plus the pOH. And so this is one way that we can interconvert between those two, okay? And then just to kind of ground you, that was a lot of math obviously there, but just to ground you in like what things are, basically once we have a 1 molar solution of a strong acid like hydrochloric acid, we end up at a pH of 0, and then things get less acidic from there. So we have some kind of common examples: wine, orange juice, coffee, rainwater, pure water, and then things that are a little bit basic: your blood, ocean water, baking soda, ammonia, bleach, all those good things, okay? And so just in summary, in case it was missed on an earlier slide, things are acidic when we have more hydronium than hydroxide, things are neutral when they're equal, and things are basic when we have more hydroxide than hydronium. And those are the corresponding pH values then, okay? That's all for today. I hope that was informative. If you have questions, please let me know. Otherwise, I'll see you in class.